Yeah, so now we've got everything for the interior. So the question now is how to deal with the top.
Right.
So if we draw the thing out again, I, J, and then K. Is this how we did it, or would you go J deep into it? I forget
Check.
the coordinates.
Um, so we did I width, J thickness, K depth.
So this is the vertical is J index and K is the depth index. Okay.
Yep, that looks
All
good.
right. And then what do we use for the number of nodes on the width?
I think it's 30.
So you did something like, I think you did something like this. So 0 to width. You said
And then
30, but what was a variable you used?
little m.
Little m. Okay.
And
And
then little m equals 30.
yeah, so you defined up here m was 30, and that gave you the x array, and then dx was presumably you did something like that, maybe.
Yeah, I have it set. Um, yeah, dx is t2 minus t1.
So the width then, that dx is going to be the if that's I equals 1 and that's I equals 2, the width of the whole thing, this is the width, I think we call it 15 centimeters or something like that.
Yep.
All right, so we've instantiated the x array, and then you did something similar for the y and the z. So now we've got to handle, and some of the other, you were saying one of the other things that you did was you set the initial temperature. You did it something like initial point in time, and then you set the other three indices. So that was our initial condition. And then
Right, for the steak being at room temperature.
yeah, at time
Yeah.
0. Yeah. That first one being the time array. And then you set, how did you set some of the sides?
So for the bottom of it, I did t colon comma colon, and then 1, and then colon.
You set it like T bottom. Okay. And then you said, so that column there was for all points in time.
Yep.
And then this was all points in X.
All the points across X.
And then this is the lowest part of Y, and then all the points in Z. Cool.
Yep.
So that effectively you're setting that plane, the bottom plane, using that. Okay. And then you did something similar for the sides.
Yeah, I did it for the left, right, front, and back.
Yeah, gotcha. Okay. So now, okay, so we've handled 5 of the boundary conditions. So the bottom, front, back, left, and right sides. And we've established the initial condition. The only
Right.
thing, the thing we got to left now, this is tricky, is to deal with the boundary condition on the top.
Where we're doing the convection.
Yeah, the top being up here. So this is going to apply, because we've got natural convection on the top. And that boundary condition, we specified it was negative k dt dy was equal to the heat transfer coefficient. And I always have trouble with getting the signs right. dt dy is going to be positive. We got a negative sign here. So this, okay, so it's going to be something like t top minus t infinity, because t top is colder than t infinity. Yeah, I think I got the signs right here. So this is going to apply, this boundary condition is going to apply at y equals thickness. Whatever you
Right.
said, however thick, that was like 2 centimeters or something like that.
Right.
And that's going to occur at what value of j? J is equal to what?
We want the maximum J value.
Yeah.
So we could use, forget what we called our value for J, but it'll be like N.
Did we use
So
n nodes vertically? And
Yeah.
you also set n was 30 to begin with. Okay.
Yeah, I did.
All right, so j equals n would be at the top. So this is how we would do it. So instead of saying y is equal to the thickness, we can also just say that applies to for when j is equal to n.
Right.
Okay, so let's discretize this then. So the way this will look, we'll have negative k, and then t I j plus 1 comma k at some point in time minus t j minus 1 at k, and we're going to divide that by delta y. And keep in mind this only applies for j equal to n, which we'll get to in a
Right.
second. Yeah. So t top j is equal to n, so that's n is the j index. So what I'm going to do now is change the j's to what, n?
Yeah.
Cool. Now, okay, so the reason this is going to be important is when we look at this discretized equation, the whole idea is we loop through I, j, and k to find the temperature at the next point in time. A problem is going to occur. Well, when we loop through I, we're going to loop through. How did you set up that for loop? You said for I equals something to something. Do you recall?
So for I used 1 colon m minus 1.
Cool. So you started at the very left side and then went to the second to last right side.
Yeah.
The reason this is handy is because we've already set the boundary condition on the right side. But
Right.
we've also set it on the left side, so I propose we go from 2 to m minus 1.
Yeah, that'd make more sense.
Alright, so that's set that, and then you also had a loop in there, presumably something looked like 4k equals 2 to n minus 1. And now, the problem is we don't know the temperature at the top of the stake. We do know the temperature at the left and the right sides, but we don't know, like, we have to do something like 4k equal probably 2 to something. And ideally we would want it. How many nodes tall is it? What index do we use for the number of nodes? We've got m across j. What do we use for j? There's n nodes tall. Is that what we did?
Yeah.
I think. And then
So
k. How many nodes deep was it?
I want to say we used 30.
30. And then what variable did you use to represent that?
I used p.
Lower, yeah, okay. So we got p nodes deep. N nodes tall. So we're looking at we're going to look at the j index. We're going to set j, the vertical. We'll start out at 2 because we know what it is at j equals 1, and that's equal to the t bottom. So we're going to come up 2 to j, because we don't, 2 to p, so the very top of it.
Right.
And there's going to be a problem. And the problem that's going to occur is here. Because that is going to reference a p plus 1, which is going to be outside the bounds of it. So what you're probably going to want to do I'm sorry, 2 to n, because we're going from bottom to top, so 2 to n.
Right.
For j. The problem that we're going to get is this right here, that n plus 1, which is going to be outside of the array. So what you're going to do is an if statement, and you're going to say, somewhere in your loop, you're going to say if j is equal to n, then what we can do is solve. We're going to say, we're going to solve for what this would be. This is a ghost node.
Right.
Because it's kind of like up here, so it's not like a real thing. So let's solve for that. H delta y over k. And then we're going to add this term. So we want to make sure, I'm assuming I did the algebra right. H delta y over negative k. Yeah. Okay, so you're going to say something like that. If j is equal to n, sometimes I might call this like T upper ghost or something like that. But you can take that value now and substitute that into here for the case in which j is equal to n.
Right. So now we're not going to be exceeding that because we know what it is.
Yeah, it lets us apply that boundary condition. We can handle it that way.